Okay, it's some random sound actually, and I want to recognize it. I want to make a post request to Google to recognize this, and it's fairly simple actually. We just make a HTTP post request to this API. We need to give the audio format and its data along with our API key. That's the key here. In fact, I can show the script. This is the script I'm using. If you look at the URL, we have to specify our language and our API key. This API key, we have to get it from the developer's console. Yeah, it's fairly simple. But if you look at the problem, we from the API key, we can only have 50 requests per day. And I don't think there's also a paid service for it. I'm not sure, but it's 50. And there's one more problem actually. We have to specify the language ENUS. If we have some less popular language, then it simply won't work. It's modeled for ENUS and some 50 other popular languages. The number of languages are infinitely more. Let's see how it's called. Now consider, to illustrate such a problem, let's consider one more problem. If we have a sound like this, so we have this sound, and we want to make it out that a dog is barking. And if we send this to the API, the developer is this reaction will be exactly like this. I designed it for humans, and you're doing it for nonsense stuff. I'm not able to handle it. So it's we can't expect it from any API. All speech recognizers are for humans, by humans. So let's actually define a problem. You have a recording, and when we have, say, I have collected a set of recordings, and I want to find out whether it's a cat screaming or a dog screaming, cat sound or a dog sound. A simple, say in my house, I have made a system where if a cat sound is heard, I have to release cat food, and if dog makes a sound, I release the dog food. That's such example. But I made it up to demonstrate why we need our custom models. The problem is the cat sounds are, whenever you speak something, if I say hello to the recognizer, my voice, hello, it's trained on my voice. My voice or other human's voice thousands of times. And whenever I say hello, it's recognized that, okay, this is similar to that word, and it predicts. But nobody has trained on cats or dogs' voices. So we can do it. It's just very small problem. If you look, I had implemented this, and if we look at the source code, it's just about less than, I think, less than 500 lines of code. There are just three files. So the way we do it is for the I have recorded in the cat folder. I have recorded 20 cat recordings. Here I have 20 cat recordings, and similarly in the dog folder I have recorded 20 dog recordings. Now the challenge is I'll train on the first 15 of these recordings, first 15 of cat recordings, and first 15 of dog recordings, and the rest 10 of the recordings I'll keep it for testing. So the very first thing I have to do is I have to get my data in proper format. The .wav file is suitable for playing it out, but it's not suitable for comparing how similar that data it is to some particular other sound. So the first thing we do is we extract the features from the audio files. I don't particularly want to explain the source code. I put it on GitHub, but what exactly we do is we take the important frequencies. There are 13 frequencies in human sound. We get those only extract the human voice at those 13 frequencies, and every 10 milliseconds we get for every, say if there's it's a 1 second worth of duration speech, we get 100 vectors of 13 dimensions. So I have written a script actually. Once I can run it. So what it does is it's error, some formatting error. But what it does is it extracts the features from the audio files. So when we look at animal features, here I have extracted the features from all those 40 recordings. It's named, the feature file is named it's actually, the features are called MFCC features. If you look at this, it's actually a NumPy vector. It's a 2D array actually. It's 2D array saved in text format. For each of those 40 audio files, we have a 2D array. We have converted a wave file into a 2D array and saved it basically. In this, when we format the data. Now, when we want to extract, say if we want to test, we'll take another sample sound, and we want to detect which animal is actually making the sound. If you look at the code, the extract features is for extracting, and extract feature directory is a wrapper over that. When we for detecting animals, it's just 58 lines. It's when we have the features extracted, it's small, so it's good. Instead of for a simple problem like this, it's good. Let's actually execute that. Say we have, let's take one sample. We are trained on the first 15. I'll test it on this one. So first, this is the one which I want to test upon. So I'll explain what the distance and all the stuff is. What it does is when we compare with there are two, actually we can model this problem as there are two clusters. One clusters belong to the dog sounds. One more cluster belongs to the cat sounds. So it's a binary classifier basically. Whenever we have a new input, we have to fit into the first class or the second class. The way I'm doing it is for each of the inputs, I'm calculating the distance from the mean of the clusters, and whichever has the lowest distance from the clusters. The way I can do all this is because I have extracted the wave file into the 2-dimensional vector. We can't directly apply this calculations on an audio file. That's why I converted it to features and calculating the distance from those features. This example worked properly. Let's try some other example. Here I have trained on the first 15. Uh, Here, if you notice the mean of the distances, it's 5. It's not units. It's just mathematical calculation. Where here the distances are lower because I've used a cat sound here. Here they are slightly higher. Yeah, it's quite efficient for a small problem like this. Yeah, this is what I just explained actually. Speech is also data. It's very similar to text data, but it's just a lot bigger. We need to format this and get into. We need to format this. It can't be directly. Cannot be directly classified. I've not explained the signal processing techniques because it's all included in the library. I've used SkyPy and NumPy libraries while calculating the distance, and also when extracting the important 13 frequencies from the speech. There's a lot of research is done based on that. I just picked out the values from those research from those papers and used those frequencies. Yeah, this is in GitHub. If you can look at it, it's a very small piece of code. It's not very big actually. Let's try actually slightly more challenging. It was too simple. When we have, if we have a cat or dog problem, we are guaranteed that the result is going to be either of those two. It becomes easier. I have created one more problem actually, where I speak a digit and I have to recognize which is it. And I'm not using any ready-made library available, because most of the libraries which I've seen make a call to Google Speech API, and it somehow defeats the purpose of having our own. The reason is I want to restrict my output to one of these 10. And if I use any library, I can't restrict my output to one of these 10 digits which I'm speaking. If, say, 1 sounds like omen, the result can be omen. But that was a bad example, probably. But it can go out of those 10 results. Let's see. So the problem is I have to speak, and I have to it has to recognize which of those 10 digits it is. Oops. So for this example, I have already extracted the features. It's exactly the same process. I'll just I'll open the source code actually. Extract features, and this is just one file here. It's actually the same file, only the input, the directory names have changed. So let's, here I've used, for training, I used 50 recorded samples, 5 of each digit from my own voice. If somebody else tries it with their own voice, it probably won't work. They have to train their own. Oops, my battery is running out, actually. Just kidding. So here I want to, I have used 50 recordings of my own voice and use them as a training. And for testing, I'll actually speak live into the microphone. Seven. Oh, recording's not okay. 7. 7. Here it's calculating the distance, and works actually. As we see the distance from the 7 is minimum. We can try on other digits as well. It works exactly the same. Here, this is actually a custom problem. It may seem very similar to what we generally use our Google Speech API with, but we have restricted ourselves that we only speak one of the 10 digits and not any other word. So it's this has many applications actually. If you notice the pattern in the first example, there were two voices and each of them had made a single sound. In this example, there was one voice, and I had to speak one of the 10 digits. Oh, there's a mistake actually. I forgot to correct that. It's actually 10 sounds. One speaker and 10 sounds. The speaker's characteristics, it's formally defined as an acoustic model, and the content what I'm speaking is a language model. So if I am speaking and if I say some other word, it's not recognized. That's because that acoustic model is not there. It's just trained to recognize, the language model is not there because it's just trained to recognize one of those 10 words. In the cat or dog example, if the cat said something else other than its regular sound, it won't recognize, but because it's trained to recognize only one word from the cat. Similarly, in the second example, it's trained only on my voice. If somebody else tries to say the same word one, it won't work probably. So that's just the formal definition of how it's modeled. In standard English, it's usually trained on a large number of speakers. It's very huge. It's hundreds or thousands. And the acoustic model, the large number of speakers are acoustic, and the language models is actually made in the form of sounds. All humans typically can make only about 44 basic sounds. Humans can't make more sounds than that. All words, if we see, are combination of one of those 44 sounds. So the way here it was a small problem. We had to recognize only one of 10 digits or a cat or dog sound. Now consider a scenario where we are in a courtroom or we are speaking in some context, and we are guaranteed that the users will speak from a selected 50 words. In only those 50 or 50 is too small. From those 1,000 words, we are guaranteed that all the people in the room are speaking only from those 1,000 words. We just want to exclude all of the remaining. So in such a case, our only solution is to use an open source recognizer and fit in our language models and parameters. Fit in our language models actually. This is a typical language model example. Here, say for an example, I'm speaking once upon a time. So what I'm trying to do here is I'm speaking to the recognizer. I want to say that I'm guaranteeing it that I'm speaking only one of these 5 words. And if I speak anything else, it simply has to reject that. If I speak some other word, say mic or something, it tries to fit into one of these words. So language model is slightly more than that actually. It also includes the transitions from one word to other. This is how it's the representation of the same graph in the script. Actually, the open source speech recognizer I used was by Carnegie Mellon. It's Pocket Sphinx. It's just it's a executable. It's written in C, I think, but it has all the interfaces. You can use it in Python. You have to just define you have to customize these parameters: finite state, grammar, and dictionary. Actually, if we look at the how to execute it. Let's take a look at the grammar. So this is a grammar file. Here the words which are there, if you notice, only once upon a time, a beautiful princess. The end is the end state. It's not actually a word. So the way how it is generated is when we have a huge set of recordings and their transcripts. There are, I think, open source tools to generate such finite state graph, or there are whatever speech recognizer you are using, it can generate such a model if you give it the transcripts. So what is basically means is from one word to the same word, this is the transition probability. To another state, it's almost the same. And when we have to run it, actually, we simply execute it, and whatever we try to speak, it tries to fit in those words. Once upon a time, the beautiful princess. Once something happened. Oops. Once something happened. Yeah. So I spoke something else, but it simply rejected. It tries to fit in once the end upon. Let's try speaking something which is within its grammar. Once upon a time. Oops. I think it's too noisy. Yeah, the upon a time. None of the custom ones are very accurate. The accuracy in what they claim is about 75%, even in perfect lab conditions. When we have it in an open space, it's quite a mess. Where it usually works very well when we have trained on large data, about thousands of hours of data, and in that case, even a slightly bad algorithm works better than the best algorithm. So when we this is the acoustic model, actually. It comes by default with the this Pocket Sphinx continuous is available in Ubuntu repositories and Arch Linux repositories. And these language models are available. It's the default for all humans. So whenever a human is trying to speak a new language, all humans can speak only 44, make only 44 sounds, but the words they speak are different. So usually the case is we change only these two parameters, and the acoustic model we use the default. So when we tried to use the Google Chrome from the browser, we had 3 problems. We have somewhat partially solved this, but it's not very accurate. If we want to, we are reaching there, but we have somewhat solved these problems. Like there are some other challenges which I have not faced for small data sets, but like one of them is endpointing. When we speak into a microphone, it has to determine when the user has, if not microphone, when we are recording on a radio, we have to determine when the user has stopped speaking and when the background noise has started. This is not the case if we are speaking into a mobile phone, because when we are speaking into a mobile phone, we actually hit stop, or it suddenly drops down the voice level, and it sort of becomes easy to determine when the human is speaking live. But if we are recording, I am speaking here, and suddenly I start a conversation with someone else, that should not be recorded, but that should not be included. It's still a challenge actually. And background noise is that's if the music is playing in the background, we have to get rid of it. I have not encountered this. And there's puffing, breathing sound. Most of the mics actually, it's at the hardware level. Like, it's not in the algorithm. Most of the mics and all the software is written such that we have to place the mic in the mouth. Not for this mic, but there are some mics which we have to place very close to the mouth, and it relies on the breathing sound which we are making. There are other channels which I have not faced, but if you try something, you'll face it. Let me know if you face anything. Yeah, that's all I have. Any questions if you had? Yeah.
Hi, thank you for the talk.
Hi.
Do you know of a speaker diarization toolkit at all, or do you have any recommendations?
Which one?
Speaker diarization is like detecting which speaker if it's a conversation. So like if you want to break it up and parse it as like, oh, all of these words came from this person and these words came from that person. Do you know anything?
I'm not exactly sure of that category of diarization.
Okay, thanks.
Are any of your scripts up online so we can kind of check out?
Yeah, all of them are on GitHub. All the scripts are on GitHub. This one, and this one.
So, what are you actually using this for?
So we had recordings where children were asked to read out certain sentences, and we want to measure. We have given them a text, and they have to read out the text, and we have to measure how good they are at reading out text, how accurate they are reading. So it's like we are guaranteed that we make an assumption that they are reading out only those. It was to check out how they follow the order for 3 or 4 year olds. They should not speak the last word first and then come back. For such a use case, we had built this one.
So that was part of your research at Carnegie Mellon, or?
It was a part of a course. Yeah, it's part of research also. Okay. Thank you.
Thank you. Thank you.